How much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters? The water is pumped to an outflow pipe 15 meters above the bottom of the tank. So let's draw a little sketch so we can see what we've got going here. So we've got a cylindrical tank, and we have a radius of 5 meters, and we have the height of this tank to be 10 meters, and then we're going to be pumping this up to an outflow pipe that is 15 meters above. Now if we looked at some representative slice here, and then we look at it with its little thickness, we can go ahead and compute the work of that. We're going to do the integral so that we can sum them all up. So we're going to be starting with the bottom of the tank 0 up through to the top of the tank 10. And we need force times distance. Well, our force here is going to be mass times gravity. The mass is going to be the volume of this disk multiplied by its density, and we've got water. So let's go ahead. The area of this is going to be circular. That's going to be pi r, which is 5 squared, multiplied by its little thickness, which is dy. So there we have volume, and mass would be volume times density, so we'll use rho for the density of water right now, and then times g to get the force. So there's our mg. We've got force. Now we need to multiply it by distance, and if we're looking here, the distance that we have to pump is, if we looked at this representative slice here, we would have to pump at this distance right here, which is going to be 15 minus the y value of the slice. So this is going to be 15 minus the y value. Now as we go to compute this integral, let's go ahead and get all of the constants out in front. We've got 25 pi rho and g. And then that would leave us this 15 minus y to integrate, which is going to be 15y minus 1/2 y squared, and we need to evaluate that from 0 to 10. So that's going to be 25 pi rho g, and then 15 times 10 minus 1/2 10 squared, and our lower limit 0, and we have y's in both places, so that part's going to be 0. So that looks like that's going to be 50, 150 minus 50, so 100 times our 25 pi rho g, so 2500 pi rho g. And our units are going to be in joules, and we're going to check that out to confirm that in just a minute. But let's go ahead and get an approximate here. So we know what pi is approximately. We'll use that in the calculator. Density of water is 1,000 kilograms per meter cubed, and our gravitational constant is 9.8 meters per second squared. So we can put all of those pieces in the calculator and come up with an approximate here. So 2,500 times pi times 1,000 times 9.8, and it looks like we get 76,969,020. And I'm telling you the units are joules, but let's go ahead and confirm that, and then we could say approximately 77 million joules. So let's confirm why our units are in joules. If you remember the definition, 1 joule was a newton times a meter. So as we look at all of our units, this first piece here was the area of these circles, and so that's going to be in meters squared. This was the density of water, so that's in kilograms per cubic meter. G, with the gravitational constant, was meters per second squared. Then this is the height. We're going to be raising that, so that's in meters. And then this would be our little thickness, so that's also in meters. So as we look at all of those units, here's a meter squared times a meter that will cancel with the meters cubed on the bottom, and we have kilogram meters per second squared right here, and that is the definition of a Newton. So that is a Newton times, we still have a meter here. So indeed, our units are joules.